Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Okay, so let's kick off our discussion about some really interesting materials that cover deep learning for intrusion detection and parallel computing in Python, focusing on processes and threads, Joblib functionalities, and even some Dask magic.
Right, it's kind of a deep dive into how we actually balance the heavier tasks versus small tasks in our code execution, isn't it?
Exactly. So, to start with, we've got the basics. A process is essentially the execution of a program, right? And within that, a thread is a single execution sequence, meaning processes handle the heavyweight stuff, while threads are perfect for those quick, smaller tasks.
I like that analogy. It's like using a full-blown truck for moving furniture versus a small van for just delivering like a few parcels, you know?
Exactly. And then they introduced Joblib, which supports both multiprocessing and multi-threading. Its behavior really depends on the backend that's being used.
Right.
For instance, the default backends include Loki, which is process-based, and threading, which is, thread-based, all on a single host. And they even mention the Dask backend if you're using distributed Python packages. That one's really neat for networked cluster scenarios.
Yeah, that's pretty cool. Wait a minute, though. Isn't it a bit of a trade-off when you think about that? I mean, using Dask, does it always guarantee better performance?
Good point. While Dask can, in many cases, distribute the workload more effectively over a cluster, it does introduce some scheduling overhead. It's all about the balance, right?
Yeah, I see your point.
Now, moving on, they dive into scikit-learn support with Joblib. They list a bunch of models like linear regression, logistic regression, SGD classifier, K-neighbors classifier, random forest classifier, perceptron, you name it. Basically, for a variety of estimators.
Right. I found it interesting that they also spotlight grid search CV and RFECV. That hints at how hyperparameter tuning is a critical part of model evaluation, yes? Absolutely.
And speaking of hyperparameter tuning, one of the recommendations was that when using techniques like k-fold cross-validation, it's probably best to assign cores specifically to the resampling rather than model training.
Yeah, that sounds practical.
Right. It's almost like saying, pile on the resources for the search process, but don't overdo it on the training side. They even observed testing with the Loki backend. Increasing n jobs beyond physical cores can, interestingly, slow things down a bit because of hyperthreading caveats.
Exactly. That's an important optimization tip. Kind of a reminder that more parallelism isn't always better. It's like, tossing too many cooks into a small kitchen.
Exactly. And then we have these SVC and KNN validation curves. They show, with varying n job settings, how validation performance curves shift. One of the SVC curves had a ready state, another with specific n jobs values, and then one with n jobs set to 1.
Yeah, that's pretty insightful.
Yeah, those graphs are quite illustrative. They show how the choice of parallelism backend and core allocation directly impacts performance. And then there's also a discussion of bias variance in KNN, which interestingly points to the use of one process handled by the OS as a baseline.
Right, absolutely. I always enjoy seeing that kind of empirical evidence. It's like it really forces you to think critically about how to set up your experiments.
For sure. And switching gears a little bit, the material also touches on TensorFlow feed-forward networks. There's an image labeled feed-forward ready, followed by one at 10 epochs, which hints at model convergence over time.
Yeah, that's interesting. Usually you want to see how quickly a network converges, right?
Right. It's like giving it a quick sprint session in training, and then for the grand finale on parallel computing, they go into Dask. This is where Python really flexes its muscle in parallel processing.
Dask is fascinating because it not only parallelizes operations over multiple cores, but also coordinates, say, many pandas data frames and NumPy arrays. It even handles datasets larger than your available memory. That's a game changer.
Definitely. They explain that Dask has 3 layers: the scheduler, low-level APIs, and high-level APIs. The high-level ones are like super user-friendly. It means that a lot of data transformations in ML workflows become much easier.
Yeah.
And the low-level APIs, they let you build highly customized execution graphs with any Python code. It's almost like having a custom blueprint for how you want your operations to be executed.
Interesting indeed. I love that part. It's like choosing between driving an automatic car versus building your own custom engine. One's easy to use, while the other offers deep control, right?
That's a solid analogy. Absolutely. And then they break down an operation into a sequence of smaller partition-based tasks. Dask reads each partition as needed, rather than loading the whole dataset into memory, which is super efficient.
Exactly.
Yeah, it's all about maximizing efficiency and minimizing memory overhead. And then they also provided some self-reading and additional resources. For example, links to comprehensive overviews on using Dask in notebooks and even some Joblib examples for distributed backends.
Right, those extra links can really help someone dive deeper into the practical aspects. One thing I was wondering though, do you think these strategies, like using cuz or n job settings, are always generalizable, or are they more context-specific?
Good question. While the recommendations are quite solid, like assigning cores for cross-validation or hyperparameter tuning individually, they do need to be context-aware. Testing with physical versus hyper-threaded cores shows that there's no one-size-fits-all.
Yeah, I agree. It's very situational.
Right, and it really forces you to benchmark different settings in your own environment. A researcher might get different speed-ups depending on whether they're using a local workstation or a full-blown cluster.
That's true, absolutely. And it also highlights the importance of having a good understanding of the specific backend being used. I mean, there's the handy low key, but then you have threading, and if you're lucky, Dask can distribute the load even further, right?
Exactly. And then, interestingly, they also talk about self-reading material that helps illustrate Dask's inner workings, like its scheduler and APIs. It's a really comprehensive overview, if you ask me. What I really appreciate is how the materials not only share the theory, but also back it up with photographic examples, charts of validation curves for SVC and KNN, TensorFlow training logs, and even visual breakdowns of Dask's architecture.
Absolutely. Visuals add a whole new dimension, right? And having those validation curves helps demystify the impact of various optimizations. It's like seeing the results directly instead of just reading about it in abstract terms.
Yes, it's like an experiment you can see in action. And one thing that caught my eye is recommending that during hyperparameter tuning, you multi-core the search process while leaving the model training single core. This kind of hybrid approach can minimize overhead from too many threads.
Yeah, that seems really practical.
Right. It is almost counterintuitive at first because one might think more cores equals more speed. But when you go too far, hyperthreading penalties kick in. Also, the idea of using Dask for cases where data doesn't even fit into memory is just phenomenal. Imagine working with massive data sets and still being able to process them efficiently without a giant server.
Yeah, super impressive. That scalability factor is a big win for both industry and research. I mean, it bridges that gap between what's theoretically possible and what's practically achievable, right?
Right, exactly. And the way the content divides Dask into high-level and low-level APIs is particularly significant, giving you both simplicity for common tasks and customization for more complex
Indeed,
workflows.
that's crucial.
Now, if I may respectfully challenge one aspect, while the recommendations are robust, do you think there's sufficient guidance on, say, handling error scenarios in distributed systems? Because when you're scaling out, error handling becomes a beast of its own.
That's a fair critique. I think you're right. While the overview provides great insights into performance and parallelism, it doesn't delve deeply into fault tolerance or debugging in distributed settings. That might be a next step for someone trying to implement these techniques at scale.
Agreed. Yeah, it's a reminder that while the theory and benchmarks are solid, practical deployment will need extra considerations, such as error handling and monitoring.
Absolutely, that's a key nuance.
To wrap up, what stands out is how the material spans from low-level execution details, like processes and threads, to high-level architectures with Dask. It's like a holistic guide to optimizing machine learning workflows in
totally
Python.
Inspiring. Agreed. There's a lot to unpack here, and each section, from Joblib's multi-core capabilities to Dask's layered approach, offers practical insights for optimizing performance on various scales.
Absolutely, it's a treasure trove of ideas for anyone working in deep learning, especially in intrusion detection and beyond. Thanks for sticking with this deep dive. It's been super engaging.
Always a pleasure. Until next time, we'll keep exploring these layers of optimization, one core at a time.
Right on. See you all next time.